Okay, so welcome to all of you for the last session of Aspen Plus Simulation Software, a basic course for beginners. So in today's lecture, we will start with a similar problem with the given in assignment 11. Are you guys, have you guys solved the assignment 11 problem of comparison of reactors? CSTR and PFR?
Yes, sir.
Okay, so I'm taking one similar problem for today. So the problem statement is ethyl acetate is produced in esterification reaction between acetic acid and ethyl alcohol. So the reaction is acetic acid plus ethanol gives ethyl acetate and water. A feed mixture consisting of 52.5 mole% acetic acid, 45 mole% ethyl alcohol and 2.5 mole% water enters CSTR model with a flow rate of 400 kilomoles per hour at 75 degrees Celsius and 1.1 atmospheric pressure. The reactor, as shown in figure 5.1, it operates at 70 degrees Celsius and 1 atmosphere pressure. So here we are given feed conditions, including mole fraction, total molar flow rate, and temperature, pressure, and reactor conditions are given. Both the reactions. So this is a reversible reaction. So one reaction will be acetic acid plus ethyl alcohol giving ethyl acetate and water, and another reaction will be ethyl acetate plus water giving acetic acid and ethyl alcohol. So both the reactions are first order with respect to each of the reactants. It means overall it is a second order reaction. For these liquid phase reactions, the kinetic data for Arrhenius law are given. So for forward reaction, values of K, rate constant and activation energy, and value of rate constant and activation energy for reverse reaction are given. And this rate is based on molarity. Composition is basis is molarity. Here K is pre-exponential factor and E is activation energy. The reactor geometry data are given where vessel type is vertical, head type is flat, diameter is 0.45711 diameter of head, diameter of that head type flat, and volume of reactor is 0.15 meter cube. So we are supposed to use a reactor model and we are supposed to simulate this process. So here what we will additionally do, we will also solve this problem for plug flow reactor and we will see what is the composition we are obtaining for plug flow reactor. Okay. So, do you guys want to solve it or should I show you how to solve it?
Yes, sir. I'll try.
Okay, Manish, are you having access or you are traveling?
Sir, actually, I'm outside today.
Yes, yes, you told me you are traveling. Okay, no issues. Dhruv, you can share your screen.
Yes, sir. Just 1 minute, sir.
Yeah, no issues. Take your time. Okay, your screen is visible. Okay, should I show you problem statement? Wait. Okay. Should I show you problem statement first? Or
Yes, sir.
are you having? Okay, I will show
Sir, I
you.
tried taking the screenshot, but it did not work out.
Okay, so try it once again if it's possible. Else I will tell you what to do. Uh, yeah,
Sir, 1 minute,
not
sir.
work. Okay, if not working, let me know. I will tell you to add values.
No, sir, I cannot take screenshot.
Okay, so let's do one thing. I will tell you. I will tell you the values and accordingly you proceed. Okay, so you can share your screen. Okay, so we are having in feed, we have acetic acid. I guess it won't work from here. Okay, from there. Go to equals option. It is better. It's acetic acid. Then ethanol. Then water. Okay, and ethyl acetate. Okay. So if you want to rename, you can do it acetic acid as AA. It will be easier to understand. Then ethanol something ETOH. ETOH. Okay, ethanol. Whatever is fine. Okay. Water is water, and last one is ethyl acetate EA. Yes. Okay. Let's press next. Okay, let's take NRTL model. Let's not go for ideal. Okay, NRTL. Now press next. Okay, estimate using Unifac. Okay, still it's showing 0, 0. Okay. Now let's go to simulation window. Okay, we will add a stir tank reactor or CSTR model. Okay, add one feed stream and one product stream. Okay, now we will be adding feed compositions. So I will tell you the values. First, just a minute. The temperature is 75 degrees Celsius. Dhruv, just give me a minute.
Sure, sir.
Okay, so this one is this problem. Okay, the temperature is 75 degrees Celsius and pressure is 1.1 atmosphere. Okay. Total molar flow rate is 400 kilomole per hour. Okay. Then I have mole fractions. 0.525 acetic acid. Then 0.45 ethanol. And 0.025 water. 5 water. Okay. So we have given our feed conditions. Now we will press next and we will be adding reactor conditions. Okay. So let's go for okay. Here one catch. Here we are given vessel type. If you remember, vessel type was vertical and head type was flat. So let's go
Yes,
for
yes, sir.
equipment based model, not conceptual model. If we press equipment based model, you can see that this vessel tab is activated. Okay. So let's first add reactor condition. The pressure of the reactor is 1 atmospheric pressure. And temperature we don't need to give.
No, sir.
Okay.
The phase is liquid, vapor or liquid?
It will be liquid phase only because it's an esterification reaction. So liquid only. Reactor volume is given to us. Just press next. It should enable. Go to again specification.
Reactor volume must be specified.
But why is it not allowing to? Oh, weird. Okay, do one thing, just press conceptual mode. Just uh, okay. Give the value of 0.15 cubic meter. Can you just go ahead, go again for that specification part? Can you show me what are the available options? Reactor volume, reactor time. No, this is fine. Okay. Okay, let's add the reaction. Is this LHHW?
Sir, it should be power law, I guess. I haven't seen the reaction.
Okay, it is power law. It is ethanol. Sorry, it is ethyl acetic acid plus ethanol giving ethyl acetate plus water, and forward and backward reaction K and E values are given. Okay, here it is told that head is off, vessel type is vertical, and head type is flat.
Head is at
Yes, add
bottom, sir.
flat, add flat only. Okay, and diameter is given as 0.45711. 45711. Okay, now press next. I guess we need to give some heat transfer values. We will just randomly give it. Just give some median temperature as 20 or 30 degrees Celsius. 30. Okay. Now press next. We will be adding reaction. Don't play with anything. Okay, we will add now reaction. The reaction is acetic acid plus ethanol giving water plus ethyl acetate. Okay. All coefficients are stoichiometric coefficients are 1. Okay. Now the statement says that both the reactions are first order with respect to each of the reactants. So what should we add in exponent?
Sir, 1 1 to A and ETOH and 0 0 to everything else.
Okay. Just add 1 1. We don't need to write 0 0. Okay.
Yes, sir.
Now do we need to add something else or we are done?
Sir, it is a backward reaction, right?
Yes, it's a reversible reaction. So we need to add ethyl acetate plus water giving acetic acid and ethanol. Yes. Now stoichiometric coefficients are 1. Here what will be the exponent?
Sir, same because first order with respect to the reactants.
Each of the reactants. Okay. So we'll add exponent as 1 1. Okay, press next. Okay. Oh, one thing. Okay, we are fine. The unit is metric. Can you do one thing from the top? Here, can you change metric? Yes. MET, metric.
Metric.
Yes. Okay, now let's add the values of K. Value of K is 2 into 10 raised to 8. 8. Okay. And activation energy is 6 into 10 raised to 7. 7. The unit
Calorie
is
per mole.
joule per kilomole.
Joule per kilo. Okay, sir.
And composition basis is molarity.
Molarity.
It's molarity only. Okay. So now let's add for reversible reaction, reverse reaction, backward reaction. Then the value of K is given as 5 into 10 raised to 7. Correct. And activation energy is 6 into 10 raised to 7. Joule per kilomole. And CI basis is molarity. Okay, so I guess we are done with our input. You can run your simulation and we can check what is the composition of ethyl acetate we are obtaining. Okay. So I will, okay, mole fraction. So ethyl acetate, can you show the answers? Okay. Ethyl acetate you are getting is 0.317403. Okay. So let's do one thing. Let's repeat this same problem for plug flow reactor. Okay, add some duplicator. Yes. Just right click and yes, reconnect destination. Yes. Feed, just add feed. CSTR in. Okay.
PFR, right, sir?
Yeah, now add PFR. In. Okay. Okay, can you rename? Okay, product is self-action therapy. Then. We will add. Okay.
Sir, adiabatic.
No, it's not adiabatic. Temperature is given to us. The reactor is operating at 70 degrees Celsius and 1 atmospheric pressure. No, it's not constant at inlet temperature. Yeah, it is 70 degrees Celsius. We did not get any option in plug flow reactor to add temperature, right? In
Sir, this is the
CSTR, sorry. In
sir
CSTR,
in
in CSTR.
CSTR. We added here. Yeah, no, yes, sir. We did not have to enter the temperature
Can you
anywhere.
can you can you do one thing? Can you just go to once again conceptual mode? Yeah, it is giving. So add here 70 degrees Celsius. Let's use this. Okay, it's fine now. Let's go to PFR. No, no. Keep conceptual mode on. Not yeah, okay. Now go to plug flow reactor. Okay. 70 degrees Celsius is 9 cent. Okay. Now press next. Okay. So here we know the volume of the reactor 0.15. So what should we do for length and diameter?
Sir, either we can solve or we
Yes,
need to solve it for the.
let's guess the length of the reactor is 1 meter. So what will be the diameter for the same volume 0.15 meter cube? Can you calculate it?
Yes, sir.
0.15 will be 5 by 6. It's 5 by 4 d square h. And yeah, this problem. Okay.
Sir, 0.1, I guess.
Diameter. No.
Yes, sir.
What is the equation? No, it's not point 0.1. What is the equation that you used?
Sir, I divided 0.15 by pi and then by 4 and then under root.
No, it is pi by 4 d square h is equal to 0.15. So you need to multiply with 4 divide by pi and then square root. Okay, I'll again check. Divide by pi and square root. Yeah, it's not 0.1. What are you getting?
Sir, 0.43.
0.437.
Yes, sir.
Okay, so add 0.437.
Yes, sir.
Okay, now let's add
And
reaction.
the sir, process stream is liquid phase.
Yes, we are only getting liquid product. The reaction we don't need to add because it is already there. Yes, so reset your simulation and run it. Okay,
Yes.
so what are you getting? PFR out is 0.31 and that for CSTR is 0.30. So we should get more for PFR because the reaction is which order?
Sir, first order.
Second order. For first order,
First order will
both
react with react. Okay, sir. Yes, sir.
first order will be same and second order you should get more for PFR and less for CSTR. Can we do sensitivity analysis to increase ethyl acetate concentration?
Sir, can we do design specification instead?
Okay, design specific.
Sir, because I have a doubt in design specification.
Yeah, sure. Go ahead with design specification then. Why do you
Sir,
add
so,
to add new block? Okay, you are doing it like that. Okay. What is the variable? Give some name.
sir, we're varying ethyl alcohol, right?
What should we vary? Okay, let's first decide what should we vary.
So,
I suggest let's vary reactor temperature.
okay,
Or
sir.
what do you want to vary?
Sir, we can vary reactor temperature and yes, sir.
Okay, let's go for reactor temperature then.
Okay, sir.
Okay, so it's a block variable. No, block variable. You have chosen something else.
Sir, blocking
Yes. Of CSTR block, which variable? Let's do one
temperature.
thing. Okay, I'm suggesting one thing. Can we do it for reactor volume?
Sure, sir.
Okay. I want to do one thing. Can we vary two variables at one time? Add to new. Just give or okay. Let's do it for one only. Okay.
Sir, can
Let's
we?
do it. Okay. Let's go ahead.
Sir, current volume was 0.15,
One
right, sir?
five cubic meter. Yes. So what should we give our target product? 0.5. Let's
5.
give first 0.5. I don't know if 0.7. Okay, let's go 0.7. Okay,
And very,
block variable.
sir, length of
Existing.
the CSTR
Mhm.
or diameter?
I guess we will directly have option of volume for CSTR. Yes. Okay, what should we, can you change the unit to cubic meter? It will be 150 liters. Okay. You can keep liter also. It's fine. It's fine. It's fine. It is 150 liter. So let's vary from
Sir, 100
obviously,
to
okay, see 100 to
100 to 300.
okay, let's go for 100 to 300 and see if we are getting it or not. Reset it and then run it.
Sir,
Oh, we
error.
are having warnings. So warning will be in this part only. Okay, can you go to design specification results? Okay, you are there only. Can you show me the results? Yeah. So it didn't work, right?
Yes, sir.
Okay, can we do first this sensitivity? Then
Sure,
we
sir.
can go for designs. So we'll get some idea. Okay. Yes, please next. Give some variable name. Yes. Type block variable of CSTR of which variable volume. What was written? It is volume only, right?
Yes, sir.
Okay, let's go from 10 to 100.
Specified reactor.
Yes, let's go for 10 to
Sir, we need to go higher than 150 because 150 liters is the
yes, yes, we
maximum we
need
are
to
already.
go. We need to go higher, but just I want to see what we are minimum getting. And from 100 to no, not 10 to 100, 10 to 300 or 400 something. Okay, yeah, it's done. Okay, number of points. Instead of give, okay, no, 400 are very less. 200 points will be very less. Go to increment of. Okay, you have given 200 points. Okay, it's fine. Or give increment
0.
of one. One or give increment of five. Five is fine. Okay. Let's define. Dhruv, I have a doubt. Okay, let's
Yes,
first
sir.
complete this. Can you go to that? I'm sorry. Can you go to that block? What was that called?
Design specification.
Yes, design specification. Sorry. Did we specify somewhere that what do we want as target? I guess that is not
Sir,
specified. Can you go to define? Yeah, here we made a mistake. We are defining, it's not a block variable, it's a stream variable. Go to stream variable from left. We need to define first our target. So that target is, what is that? It is a mole fraction or stream variable. Choose stream variable if it's available. No, no, don't go for mole fraction directly. Stream variable. Yeah, choose first stream variable. Then of which stream? Product stream. That is, I guess, CSTR product. Yeah. And variable is what is the variable?
volume.
Mass.
Volume.
Uh, no, no.
Mole.
Mole fraction. Yes. Yes. Okay. So we mole flow, no, not mole flow, mole fraction.
Sir, mole fraction is not.
Can you go up somewhere?
No,
It
sir.
should be there. Can you go up somewhere? It should be fraction. No. Yeah, here only. Can you go from
Molar
top?
liquid. Molar liquid
Yes.
fraction.
Yes. 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 What we did actually, we gave our target also volume and varying also volume, so it didn't work. You go to sensitivity and deactivate it. Let's see what are we getting. That was the issue. We did not get result. Okay. Why is it still showing required input incomplete? Go to model analysis tool. Just delete it. Just delete it. It's still this is weird. Okay. Reset and run it. Okay, we have error, so that is fine. So
Sir,
error
in the
should be
for the assignment also I was doing yesterday, I
yes.
was getting issue with the design specification.
Okay, first let me show here and then I will ask you what is the issue that you are facing.
Okay.
Go to results of that design specification part. Not here from there. There only will see somewhere. Yeah, here solver one. Okay. No, it's still something wrong. Go to input. Something is wrong. Go to vary part. No, no, no. There is something still wrong. Can you please go to define? We are not defining. We are not defining which is the stream, product stream, but we are not. Can you go to substream? What is the written substream?
Mixed.
It is mixed. Uh, I guess there is something wrong. Instead of stream variable, can you choose mole fraction there only? It won't work. Yeah, yeah. Now it's fine. Acetic acid. Ethyl acetate. Ethyl acetate. Yeah, now it's correct. Now it's correct. First reset and then run it. It is better. Okay, then you ask me what was your doubt for assignment. Or I have your file. If you want, I can open it. Not here. Their sensitivity, that design specification results only. Okay. So what are we getting? Okay, so we are maximum getting 0.31 only. We are not getting
Higher than yes, sir.
more than that. So volume will not help. We can play with some other variable like temperature.
Sir, I
And we'll
don't think
see.
this is not volume. This is the mole fraction, I guess, from the result of the CSTR.
Yeah, yeah, that is mole fraction because you wrote their react volume, so it's
Yes, sir,
showing
but
as
it
react
is this
volume.
one. Yes, sir.
So we are not getting more than that
0 point.
31, 31,
Yes, sir.
23, 25, 37. So volume is the limit. So we can't play with volume. We can play with some other parameter like temperature or something else to see the effect of product composition. Okay, you can ask me your doubt. What is your doubt in design
Sir, when I
specification?
was doing the design session, it was showing error between substream and like the it was showing the difference in downstream and substream. Like the
Okay.
defined variable is downstream.
Okay, if it's fine for you, can you show your problem?
Sure, sir.
Okay, I will open the problem statement. It is here. Let's check from beginning only. I suggest. It is week 11, right? Yes. Uh,
Sir, I'm opening in my
is it week 11 or 12? Week 11, right?
like 11, yes, sir.
Okay. Okay, what is the deadline for submission tonight only, right? Or did they increase deadline?
I haven't saved the design specification part yet, but sir,
Okay, do it. Okay, do it in front of me. What is told to you in question? Do you want to
sir,
check
we
everything from first or?
sure, sir.
Okay. N-butane has to be reversibly isomerized to isobutane in plug flow reactor. The reaction is to be carried out adiabatically in liquid phase under high pressure 20 bar. The feed is 200 kilomole per hour of a mixture made up of 85 mole percent N-butane and 15 mole percent isopentane, which is considered an inert. The feed enters. Okay, so we have feed conditions. Everything feed conditions are available. You are supposed to use chemical with metric units. I hope you are using that only. Yes, MatChem you are
Yes,
using.
sir.
Pang-Robinson equation of state and 3 and 1.1 meter. Okay, everything is given.
Selected
So,
method is Spang Robinson.
okay. Okay, tell me what are you facing? Where are you facing the issue?
Sir, when I'm trying to do convert for the conversation to be 70%, we have to put the design specification in the CSTR.
Yes.
So for the CSTR, the product that is there, that needs to be a certain amount. I was trying to do it, it was not occurring.
Okay, I'm not exactly understanding your issue. Can you do it? So I will. You won't be
Yes.
getting any conversion. If conversion is there as a variable or not, I guess it won't be there. Or it
So
is
no,
there.
not conversion, but isobutane, if we vary the product that is formed,
Yeah.
then it should show, but it was not
Yes.
showing.
So see, conversion is 70%. So 1 minus C by CF is 0.7. 1 minus, just give me a minute.
Yes.
1 minus conversion of, okay, let's assume conversion of n between 1 minus C by 1 minus 0.85 by Okay, how did you define conversion?
Sir, 1 minute.
You check your all
Sir,
inputs.
this
Okay.
is the initial answer, I guess.
Okay, I have not solved. So whatever you are saying, I am assuming it's correct. So now, what is the conversion here? 1 minus point,
Five
okay,
five.
0.559178. I am not checking your inputs. Okay, so if there is something wrong with input, I can't help. Okay, it is 34% conversion, right? Now, your conversion is 70%. So zero point 0.7 is equal
Sir,
to,
sir, we will subtract from 0.85 because 0.15 is inert.
wait a minute.
In the question, it is specified that it is inert.
Okay, 0.85 is inert. So it will be there only. Okay, so what are you suggesting? I'm not getting your point.
Sir, so you are using the formula 1 minus 0.55, right?
1 minus 0.55? Yes.
Conversion. Will we use that same formula or will we change the formula? We'll like,
See, what I just know, whatever value you are getting, and what is the percentage of inert?
sir,
0.15.
fifth. Yes, sir.
I need to see this inert part. I don't remember.
In the question, it is given, sir.
Yes, yes, yes. Can you just give me a minute? I will open that
Sure,
chapter.
sir.
I don't remember
Sir,
this part.
I'll come back in sir 2 minutes, sir.
Okay, no issues.
Sir, you are not audible.
Hello.
Yes, sir.
Yes. Dhruv, I will just share my screen to show you that epsilon part. Or I
Okay,
can
sir.
just tell you epsilon, in this case, your epsilon value is zero, so it won't affect because of inert. Your conversion will be 1 minus Ca by Ca0 only because your epsilon is zero. One mole is converting into 1 mole only. That's why.
Okay, sir. Okay, sir.
So
Sir, this.
you can check this from Levin's chapter 5.
Okay, sir.
Okay.
So it
Your
will be
epsilon
one.
is, yes, 1 minus Ca by Ca0. Hello.
Yes, sir. Yes, sir.
So in this case, your conversion will be 34%, I guess.
Minus 1 minus 0.56 divided by 1.
66%, sorry. No, it's 34%. 0.339. Okay. Right or
Okay, sir.
not?
Sir, yes, sir. Okay, 34.2% is the conversion. Okay, sir.
What did you do? 1 minus 0.56155 divided by 0.85, right?
Yes, sir.
Okay, now for the second case, it is for CSTR. So your conversion is 0.7, right? So 0.3 will be Ca by Ca0. So 0.85 into 0.3. So your target should be 0.255 CSTR out,
Okay.
right? Just check it
Yes, sir.
once.
1 minus 0.255 divided by 85.
Are you getting what is the 70% or oh, it is 70%. Okay. So 0.3 into 0.85. Yeah. Is this correct or not?
Sir, when I'm doing 1 minus 0.255 divided by 85 into 100, I'm getting 0.87.
1 minus 0. Sorry,
255 divided by
0.85.
85 into 100, I'm
0.85. It
getting.
is
Yes,
0.85. 0.85. 0.255 by 0.85 is 0.3 and 1 minus 0.3 is zero point 0.7. So it is 70% conversion, right?
from calculator, I'm getting 87%.
No, no. What are you doing? It is 1 minus Ca by
1
Ca0
minus.
into 100 is equal to 70. 1 minus Ca by Ca0 whole term into 100 is equal to 70, right? So you should get
Yes, sir.
0.255 only. Check it again.
Oh, yes, sir. Yes, sir. Now I got perfect.
Okay, so what was the doubt now? I am not getting.
Sir, when I was doing design specification, it was not working for me and it was showing error.
Okay, do you want to do it right now? I don't have
Sure,
any
sir.
issue if you want to do. Okay. But I suggest you once again go to that Levenspiel chapter 4 and 5 and once again check that epsilon concept. For this case, epsilon is 0. So your conversion will be Ca minus Ca0 by Ca0 plus epsilon A xa and epsilon is your 0. So
Okay, sir.
it is just 1 minus C. Just check it again. But I suggest you to just check it again. Okay, you can add your. I don't know the answers, but whatever you are doing, if your inputs are correct, your answers will be correct. Mole fraction, product. Okay, CSTR out of. Right, target is
And
0.7. Go to define. Go to define. You are specifying mole fraction, then why should it be 0.7? 0.7 is your
So it's
conversion, not your.
0.25, 0.255.
Yes. Now go to vary. What are you
Very
supposed to vary? Reactor volume, I guess.
the variable is block variable.
Block variable.
Block CSTR variable volume.
Volume. What is given to you? You are not, you are supposed to report in cubic meter.
Done.
Okay, run it. Reset and run
Now
it.
it is running. Now it is running.
Okay, see, I don't know the answers and your other inputs. Assuming that your other inputs and everything is correct, your answer will be correct. Okay. Just check everything again, your inputs. And that
Yes, sir.
epsilon part, it is zero only, so you don't need to. But once again, go through 11 spelling. Okay.
Yes, sir. It
Okay,
is running
so
now. Yesterday it was showing an error.
okay, but now it's clear, right?
Yes, sir.
Okay. Okay, so I will reshare my screen. Okay, so now we can go for our case study 7. That is for ammonia production, not through Haber process, but it is some chemical equilibrium. An inlet stream H here supplied at 80 Fahrenheit and 300 psia is compressed to 4000 psia by the use of isentropic compressor B1. The stream H has component-wise flow rate shown in the figure. So we are given nitrogen, hydrogen, ammonia, and carbon dioxide. The flow diagram for the ammonia process is shown in this figure. So this is the flow diagram. Stream F1 is mixed with the recycled stream F8 in a mixture block B2 operated at 4000 psia. So this stream F1 is mixed with this recycled stream F8. This mixture is operated at 4000 psi. Before introducing into the reactor, the mixture effluent F2 is heated in block B3 to 900 Fahrenheit at 4000 psi. So here we are increasing our temperature to 900 Fahrenheit. Note that the reactor R Gibbs before runs at 900 Fahrenheit and 3970 psia. So this is 900 Fahrenheit. Reactor conditions are given. In the next, reactor outlet F4 is cooled in a heat exchanger B5 operated at 80 Fahrenheit and 3970 psia. So this is at 80 Fahrenheit and 3970 psia. The flash drum B6 produces stream B1 and F6 at 80 Fahrenheit and 37. Then we are going for flashing operation. So for flashing, we will be getting two stream. In the subsequent step stream F6 enters the splitter B7 and 0.01% of it is used as purge. So this is splitter. Some part is taken out and another is sent back to the recycle loop. Okay. Finally, an isentropic compressor B8 has discharged the stream F8 to the mixer block B2 at 4000 psi. That is our required condition. Using the NRTL thermodynamic model and Newton's iteration method from data browser, choose convergence slash con options, simulate the ammonia process to compute the component-wise flow rates and composition of all the streams. Is this problem statement clear?
Yes, sir.
No reaction is given to you, right? N2 plus 3H2 gives to ammonia. It is not given to you. But even if it is not given to you, you can simulate it without reaction. Why? Can anyone tell me? Okay, let's go to the simulation part. I will show you. We will not be adding reaction. We are using our Gibbs. So okay. Do you want to solve it or should I show you how to do it? Okay, I'll show you. Aspen. This is a good problem. If you want to take the screenshot, you can just wait a minute. Okay, if you want to take the screenshot, I will keep this here. Dhruv, are you going to solve it with me? Or
Yes, sir.
so if you want, I will tell you to go for that design specification part. Okay.
Okay, sir.
Do it with me. We will
Yes, sir.
be starting with. Okay, let's first add component nitrogen, hydrogen, ammonia, and carbon dioxide. Oh, it's taking time. Just wait for a minute. It's taking longer than usual. I'll just stop sharing my screen for a minute. Mm, okay, so now let's add our components. Okay, we have nitrogen and two. Why is it taking so long just to add into?
Sir, what is the property method?
It is
Sir,
NRTL.
share my screen only, sir. If
No, no,
that
it's
works.
fine. It's fine. It's fine. N2, H2. Actually, my laptop is full right now. That's why it is facing NH3 and CO2. Okay, these four components we are supposed to add. I guess I will have to just give me a minute. I will just give me a minute. I will. Okay, you are not even. You are not allow. Okay, are you able to see my screen? No, right?
No, sir.
Okay, so we have added these four components N2, H2, ammonia, and CO2, right? Now we will press next. So property method is NRTL. Okay, so NRTL is here. Mm, I will have to just give me a minute, guys. I will just shift some of my not important files. Just give me a minute. Control A, Control X. Uh, it's because of that only. My screen is not visible, right? Or is it visible? No.
Not visible, sir.
Yeah, yeah. Just give me a minute. I'm sorry, just give me a minute. Okay, I guess now we are fine. So I will share my screen. Okay, I guess it is visible to you. Okay, so we have added NRTL model. Now I'll press next. Okay, so all input is there. So okay, let's try to recreate the flow sheet that is given to us in the problem statement. So first, it is being passed to compressor, mixture, heat exchanger. Okay, let's add these three first. Pressure changes. Then we will add compressor, then mixture and exchanger. Okay, first three we have added. B1, B2, and B3 we have added compressor, mixer, and exchanger. Then we need to add R Gibbs model. So we will go to reactor and we will add this R Gibbs model, that is B4 block. Then we will go to again exchanger, flash drum, and splitter. Exchanger here and flash drum and splitter. And sorry, then it is a compressor again. It is compressor. So we'll go to pressure changer and we will add compressor. Okay, I hope you added this equipments. Now we will okay, and here to here, here to here, here to here. Okay, it's a mistake. Reconnect destination to here and again here to a flash drum. From flash drum, one part is going to splitter. It is going back here. Now one stream is going out and one is again added to compressor. I need to reconnect it. Reconnect destination. Okay. And okay, let's keep it like that only. And from compressor, it is recycled back to this thing. Okay. Uh, we'll just give the name as it is given H. Then F1 to this is H. This is F1. This is F2. This is sorry. This is F3. This is F4. F5. Okay. Now F6 and F7. This one is F6 and this one is okay F7 and F8. This is B1 and oh, B1 won't work because B1 is already a name. Okay, so let's keep it as P1 and P2. Is S9 is below. Dhruv, did you do it or?
Yes, sir, I'm doing it.
Okay, I will wait for a minute. I will wait till.
Sir, I've done the, like, I've put I'm inputting the feed, sir.
Okay, you are inputting the fields. Okay, so your flow sheet is complete, right? You have
Yes, sir, yes, sir.
Okay, so let's go for flow input conditions. So H is 100 pound moles per hour. We have to add flow rates, molar flow rate. So N2 is 100 and 300, 0 and 1. 100, 300, 0 and 1 with 80 Fahrenheit and 300 psi. 80, 300. This is Fahrenheit. This is PSI. Okay, so H input is given. Please cross check your inputs. Okay, then we will be going to compressor part. Wait for our Gibbs model. Okay,
Okay, sir.
4000 PSI is isentropic compressor
Discharge pressure.
with discharge pressure as 4000 PSI. Okay, then mixer is also at 4000, I guess. Sorry, mixer is at yes, it is mixed operated at 4000 psi block B2. That is mixer.
Sir,
It is
could you
4000.
show this part? Could you show this part of the statement again?
Okay, just give me a minute. I will show it. 4000 psi. Nag is valid phases are vapor only, not vapor liquid. But it won't matter. Okay. Have a look.
Done, sir.
Okay. Now it is heated to 900 Fahrenheit and 4000 psi. So here 900 Fahrenheit and 4000 psi. Okay. Then okay, now we are at Gibbs model at reactor part. So we don't need to add any reaction, right? Can you see any option of adding reactions here? I guess no. No reaction is given, right? Then how will it calculate amount of ammonia? How will it calculate amount of ammonia? T970. Any idea?
They're using Gibbs energy.
Yeah, using this equilibrium. What we are saying, calculate phase equilibrium and chemical equilibrium. Then when there is N2, H2 and NH3 as a mixture, it will find a point with minimum Gibbs free energy when ammonia is formed. Okay, so it will automatically take it as ammonia as a product. It will calculate this equilibrium and from that equilibrium, it will say that ammonia is product. So we don't need to mention any reaction here. Now, moving ahead, I guess it's same. 80 Fahrenheit and 3970 psi. 80 Fahrenheit and 3970 psi. Block B5. Then block B6 is a flash drum. I guess it's the same condition. 80 Fahrenheit, 3970 psi. Okay, log B, this flash drum. Now for splitter, what is told? 0.01% of it is used as purge, which will be the purge stream P2, right? And it is 0.01%. So 0.001, right? 0.01 or 0.1.
So
It is
0.01.
0.1. So 0.00001, right? We just need to use plate breaks.
0.01%.
0.01 into 100. 0.01 by 100. So that is 0.001, right? Am I right or not? Then compressor is operated at okay 4000 psi. Isentropic compressor with discharge pressure of 4000 psi. Okay. So our required input is complete. So okay, I don't need to reset. We'll just run it. So we'll be throwing out with some errors. Let's wait. Okay, some errors are given. And what is the error? Bro, were you able to complete the flow sheet or you are still left with it?
Sir, same error.
Okay, there is convergence error, right? It's not converged.
Yes, sir.
So here in problem statement, what is told to us? That I think minimized, I don't know. Okay, using the NITL thermodynamic model and Newton's iteration method, simulate the ammonia process. So whatever the by default convergence method, it is not working. So we are supposed to use Newton's iteration method. So from where can we add that method? From where can we add that? You guys know?
Sir, convergence.
Let's change
Sir,
the
when you go
method
to
here.
convergence, sir, there are different methods in the drop-down menu.
So here we will choose Newton. Just a
From
minute.
data.
Here I guess you need to somewhere you need to change it to Newton default. Yeah, here in default methods, just change it to Newton everywhere.
Okay,
Did you
sir.
find it?
Yes, sir.
Just change it to okay. Wherever it's not, just leave it. Here for optimization, it's not Newton, it's SQB complex or something else. So let's add Newton for these four parts and run our simulations. Okay, so now we are having results without any errors. So now let's see what is the value we are getting. So if we go for block, okay, P1 and P2, we require P1 and P2. So from flash drum, we are getting maximum amount of ammonia as P1. And what was P1? P1 was bottom part. So we are getting maximum amount of ammonia out of what is ammonia generated after reaction. So at ammonia at stream number F4 is very irritating. Ammonia at stream number F4 was 1979. And what are we getting? 1525. So rest is going in top stream, that is F6. So that part is being recycled.
Sir, I'm getting ammonia as 1979 kg per hour.
1979.
Kg per hour, yes, sir.
In
F4.
which
Yes,
stream?
sir.
F4 is
F4,
fine.
F4.
P1, I'm saying P1 stream. P1 means after
P1.
flashing. we are separating N2H2CO2 from ammonia. So after flashing, you are getting 1252.52, 1525.52 kg per hour, right?
Wait, sir, I'll check results of
Okay. Stream P1.
B1. Yes, sir,
After
1525.52.
Okay, so we are getting maximum amount of ammonia from here, and other whatever N2 and H2 is not reacted, we are giving it back to the recycle stream after compressing. Okay, so you can see it F8 stream. We have additionally 450 and 1351.67 kg per hour of hydrogen. So hydrogen at F2 is 1625. Hydrogen at F2 is, so it is F1 plus F8. F1 plus F8. Okay. Do you want to do sensitivity or something else? You can share your screen. Okay, so what should we do? We have, we can increase amount of ammonia. Let's play with flash temperature, because flashing is the part where N2 ammonia is being separated out from unreacted N2 and H2. So can we increase that? Uh, can we
Oh,
increase
sir.
that?
Design spec or sensitivity analysis, sir?
Whatever you want to do. Okay, go for sensitivity then. Give some variable name. Okay.
Stream variable
Of
of stream.
which one is the stream number?
Sir, B6.
Not
No,
B6, it is
B1 generated
B1.
B1.
Yes.
Variable is mass flow.
What
Mass,
was the mass fraction value?
mass fraction value.
What is the mass fraction?
Sir, ammonia is 0.97.
So let's go for 0.99 if you are getting, or 0.985. Mass
Sir,
fraction. Go
start
for mass
temperature.
fraction. Go for mass fraction.
Mole flow, V fraction.
No, that is molar fraction. Okay, you can also choose for molar fraction. So mass fraction, can you see somewhere?
No, sir, and these are the only options that are available.
No, wait. You are doing sensitivity, right?
Yes, sir.
So first you need to your block, it is your block variable. You are varying either temperature or pressure. So you need to first vary. See, your tab is vary. So you need to
Flash block, variable, temp, night.
okay, what do you want to play with? Temperature or okay, what is the just
Sir,
give me what is the temperature?
sir, 80 degree Fahrenheit.
Uh
We can
just
vary it between 70 and 100, I guess.
okay,
And increment of, I'll say, 1.
70 to 100. Okay, increment of one. One is fine. Then let's go to define. Define means we will be defining what
Yes, sir.
what we want to vary.
Ammonia. Sir, so what we want to vary is already in the temperature. Define is
Sorry, what do
what we need.
yes, yes.
NH3 mole fraction.
Just I'm sorry. Can you go to again vary? I guess we are messing up something. Wait. Vary means what are we varying? So we are varying temperature. Yeah, it is correct. It is correct. Now we are defining. What do we want to see? Ammonia mole fraction or mass fraction. So it's a stream variable. Yeah, it's correct. It's correct. Just be careful with these words. Very defined. Mass
Okay, so
fraction. Choose mass fraction of
stream will
stream
be B1.
B1 of component. Which component? Ammonia, right?
NH3, yes, sir.
Okay. So let's go to tabulate part. See how we want to tabulate it.
Run, sir.
Yeah, done. Reset it and run it. So see what are you getting? Are we getting it?
Sir, the temperature is being varied from, yes, sir, Celsius.
Okay, it is in Celsius. Okay, are we getting point? What are we getting? Can you go
Sir,
below?
the maximum we are getting is 9.97.
Yeah, so increase in temperature, it's not point. This won't increase because it's a R give, so it won't temperature is it won't play a major role.
Sir, so can we vary the temperature of
Go to
the
design
reactor?
space. No,
Designs.
design reactor temperature you want to vary. What is the value right now? It
Sir,
is
for
it is already at 900 Fahrenheit. It's fine. Reactor temperature won't affect. Do the same exercise with this part only with flash temperature.
so variable is flash temp.
No, here first is defined. Be careful.
So
Here it's first
NH
defined. Yeah.
NH3 mole fraction.
Yes.
That is the stream variable. Type is mole fraction. Stream is B1
V1 stream
component.
of component ammonia. Then we need to specify it. So just write something. Okay.
The target is, sir, because we got 0.97 already. Can we put 0.9598?
Okay, 98. 985. Keep
985.
it 985. I guess we won't get it, but let's try it. Okay. Vary.
Very
What are we supposed to vary? Block
block
variable
variable.
of block
Flash
plus
temp.
temperature in Fahrenheit from it is 80 right now. 120. Go to 120. 125. And then reset it and run it. See, I don't think we will get it. Hello.
Errors. Errors, sir. Yes, sir.
It's not visible. Your screen is stuck right now. At least for me.
Is it visible now?
Not yet.
There is some network issue, sir.
Okay, so you're getting errors, right? You are not getting.
Errors.
Can you try it again? If it works, it works. Else it's fine.
So can first I need to deactivate the sensitivity, I guess.
Okay, do it and then again try to share your screen. Okay.
So is it visible now?
No. Okay, it's fine. But you know how to do it, right?
Yes.
So you're getting error because of you. What is that design specification giving you maximum amount of what is maximum mass fraction you are getting from there?
From design specification.
Yes.
Sir, the maximum I'm getting is 0.972 at
Oh,
51 degrees Celsius of temperature of flash.
Okay, then leave it. So we are, the problem is anyway at its best. Okay.
Oops.
You know, but be careful with this what vary is written and define is written. Okay, vary means what variable you are varying, and define means what purity or what whatever something you
Is
want to
required in the
define.
question. Okay.
Yes, yes. Just be careful with those words. Yeah, now it's visible. Now your screen is visible.
So there are two errors.
Convergence issue. Is this design specification?
Yes, sir.
Results, can you show me the results? Okay, it won't give you maximum. So it's fine. It's fine then. No issues. Okay. So, okay, let's do one thing. I hope this problem is clear. So now moving for the last problem of this whole session. I have already solved that problem. I will not show how to, I will not solve it right now because it's very lengthy. It took me to solve around 1.5 hours. So we'll not be solving it right now, but I will show you. What is the problem 4.4? Okay. I'll just share my screen. Just give me a minute. Practice 4 point. Okay, reforming problem. Okay. Okay, I'm sharing my screen now. Okay, is my screen visible?
Yes, sir.
Okay, and Aspen window is also visible. Okay, so let's first read the problem statement. Okay, the case study, last case study, Aspen plus simulation of PETLYUK column with streams recycling. There are multiple recycling here. Let's read first problem. Naphtha reformate is extracted from four aromatics and the aromatic compounds are fractionated into benzene, toluene, and xylene in sequence. So what we do, naphtha reformate, we extract it from aromatics, is extracted from, it is not four, it is, I guess, okay, it's four. And those aromatic compounds are fractionated into benzene, toluene, and xylene in sequence. This separation is conventionally carried out using a series of binary-like columns. In order to improve the thermodynamic and economic performance, Lee et al. Proposed a fully thermally coupled distillation column, which is also called PETLYUK column. Originally, the first two columns of the conventional process flowsheet are suggested to replace with this column in 4.36. So there are two columns we need to follow. One for fractionation, as the problem statement was saying, and one for this benzene, toluene, and xylene product. But instead of using these two columns, we can use one column that is called thermally coupled distillation column, and it's the name of this. So we are going to simulate this part. So the molar flow rate of liquid feed stream, namely feed entering at 132.3 degrees Celsius and 150 kilopascal, is provided component wise in table 4.4. So here feed. So let's first understand this flow sheet. So feed, we are adding something in feed. So from feed, we are fractionating it. So we will be getting from something from top and something from bottom. From top, we are getting vapor. We are compressing it and we are passing it to a distillation column. Similarly, bottom, we are passing it through the pump and adding it to a distillation column. So from here, we are getting some D, S and B product. D is distillate, B is bottom and S is side stream. So here, what is the game? Game is recycling. So from distillation column, from one of the tray, we are recycling back something into this reformate, and here also we are recycling back into recycling back something here. So composition. So don't get afraid. This is the product. These are the reactants, not reactants, but this is what we are having. What is it called? Naphtha reformate. So here we have benzene, 2,3-dimethyl pentane, 2-methyl-hexane, toluene, N-octane, ethyl benzene, paraxylene, amxylene, metaxylene, orthoxylene, N-nonene, N-pentyl benzene, 1-methyl-2-ethyl benzene, 1,3,5-trimethyl benzene, 1-methyl-2-N-propyl benzene, ortho-diethyl benzene, 1-methyl-2-isopropyl benzene, 1,2,4,5 tetramethyl benzene, and pentamethyl benzene. So here we can see that what is the maximum amount. Benzene 87.45, toluene 338, and amxylene 128, and some other components like paraxylene and orthoxylene are also in good quantity. These 1,2,1,3,5 trimethyl benzene, 1-methyl-2-ethyl benzene. So there are these are the major components, and from here we want benzene, toluene, and xylene BTX product. So table 4.5 specifies other two input streams introduced to the pre-fractionator before connecting the recycle stream. So here is the game. So you can see that this one is actually a very complex. We are having many components here. So it is not advisable to directly connect when we are simulating. It is not advisable to directly connect this stream with here and this stream with here, because there are higher chances that your simulation won't converge. So what do we do? So for that, what are we told? These two recycle scheme, PB2 and PD2. Assume it that it is like this. It is like this, that PB2, whatever we are getting, we are this recycling from here. I am giving it as a separate stream, and whatever we are recycling from here, I am giving it as a naming it as a separate stream. Okay. Okay, I did a mistake actually. Okay, yeah, I have added it. PB2 and PD2. These two that we are adding it to the here. I am currently naming it here as PB2R, PD2R, and here PB2 and PD2. Okay. So we are not directly, we should not first connect for these complex problems. So this is the initial gas given for PD2 and PB2. For that gas temperature, gas pressure, and gas molar fractions are given. So we will take this as our initial gas. So what should we do? What should be our strategy if this PB2 and PD2 initial gases are given to us? Can anyone tell me? Did you understand problem at all, or was it
Sir,
very
it is a
difficult?
bit tricky.
Yes. So what they are trying to say is what is given to us here in question. We are given some PD2 and PB2. So let's say from here I input this PD2 and PB2 value given in the problem. Okay. So
Yes.
ideally, what should we get? This PD2 PB2 inlet should be same as PD2R PB2R output. Do you agree? We should get this PD2 PB2 and PD2R PB2R same. Do you agree?
Yes, sir.
Why
Same
do we
same
get it
input as
same?
output.
Yeah, because we are supposed to add it to the here. Okay, are you getting my point? What I am trying to say?
Yes, sir. Yes, sir. It is a recycle.
Yeah, so these two input should be similar to these two output. So
Out.
that's why some gas point is given to us. And first we are uh, some gas point is given to us and we will simulate it. Then what we will do, obviously our gas point and this PD2R and PB2R will not be same at initial point. So what we will do, we will take this once first after first simulation, what we'll do, we will take this output and we'll give it here as input PD2, PB2, and we will resimulate. So we will repeat this problem, we will repeat this process until and unless we are getting these two streams equal. Okay, or not? Hello? Please say if you are not getting it. I will re-explain.
I'm getting it, sir.
Okay. So you understand the complexity, right?
Yes,
So
sir.
these PD2, PB2 initial gases are given to us. I'm sorry, where is my cursor? I can't see my cursor. I can't see my cursor. Just a minute. Uh, okay. So here I'm not able to see it. I don't know why.
Sir, it is in.
Yeah,
Sir, you
not right now.
you
Yeah.
hit the cursor, sir.
Yeah, here I can see it, but not. I. Okay.
Yes, sir, it is back.
So do I need to? Yeah, again it's invisible. Why is this happening? I don't know. So okay. So here we are given conditions for this prefrag and main columns. Our two column, one for prefractionator and one for this thing, main
Yes,
column.
sir.
So we are supposed to simulate this. So I have already simulated it, but I will just show you. I'm just trying to give control. Yeah, why it's not working? Okay, I'm giving you control through. Can you just open this Excel file? Sorry, Aspen file.
Sure, sir.
Yeah, that one. Yes. So here, okay, now it's fine. So here, according to the uh, according to the problem statement, we have prepared the flow sheet, right? So okay, one more catch. This prefractionator, what was the model for that? It was not mentioned, I guess. But for this, we have taken this red frag column with no reboiler and condenser. And for this, we have taken same red frag but with both reboiler and condenser. So let's go to first feed stream. And we are supposed to use unifag model. Unifag or unique Unifag model. Okay. So here you can see that feed is at 132.3 degrees Celsius from problem statement and pressure is 150 kilopascal. Yes, pressure is 150 kilopascal. Okay, I will show you the problem statement again. 132.3 degrees Celsius and 150 kilopascal pressure, correct? So that we have given as our this feed stream. Then what else is given to us? This huge table containing molar flow rates in kilomoles per hour for all these components. So I added all these components and then I added the molar flow rate in kilomole per hour. So I added this thing. Okay, this feed stream is clear to everyone.
Yes, sir.
Then we gave our input to this red frag column. So we will go to the inputs of red frag column. It says that prefrag column 22 number of stages. So we have given 22 number of stages. You can see it here. Then no condenser and reboiler. So we have given condenser as none and reboiler as none. Okay. So for this, it's clear. Now we will go to streams part. So for streams, we will just do the way it is told. Entry of feed stream, seventh stage above. So feed is seventh above stage. Then PD2 is first stage above and PB2 is 23rd stage
Yes.
above. Okay. And exit PD1 is first stage, that is vapor. Okay, this is by default. This is we are not adding, but we are just checking. And PB1 is 22 stage and liquid. And column pressure is given to us as 70 kilopascal. So this is what we just added for prefab column. So this is for PB2. PB2 is coming from bottom and PD2 is adding from top. That's why it is 1 and sorry, not this one. Yeah, that's why it is 1 and 23. Okay. So this part is clear. Now we need to let's see first these two gases for PB2 and PD2 stream. So for PB2 stream, initial gas was given to us as 115. No, sorry, PB2. It is PB2. It is 155.4 and 177 kilopascal. And this molar fractions. Okay. So these two values, molar fractions and some flow rate. Flow rate is not given here, but flow rate is mentioned here. That PD2 and PB2 stream are fixed at 290.1 and 492.9 kilomoles per hour. So from here, we added this molar flow rate and compositions. Okay, then one more thing. Here it is told that the stream is vapor stream, right? Here you can see that phase is vapor phase. So what do we need to do? We need to go to flash options, and here in valid phases, we need to add vapor only. I guess by default it is vapor liquid. You need to check and you need to add here vapor only. Okay, as it is mentioned. On the other hand, for PD2 stream, temperature is 115, pressure is 110 kilopascal. These molar fractions are given, and here molar flow rate is 290.1 kilomoles per hour. So we added 290.1 kilomoles per hour. Here, no valid phases. We are not given anything, right? Here you can see nothing is written. So we will just untick this, uncheck this part. Okay. If I do this and it's like this, earlier it was like this. So I just need to uncheck it. Okay. For this PB2, it was vapor only. Is this clear? Till here, is this clear? Is this clear? Please say yes or no.
Yes, sir.
Then we have pump. Discharge pressure of both the pump and compressor are 120 kilopascal. So for pump, it is 150 kilopascal. And similarly for compressor also, it is, sorry, it is 120, not 150. I spoke 150. It is 120 kilopascal, right? Now we need to check input for three stream. So here we were given 89 stages, including condenser and reboiler. So 89 stages, including condenser and reboiler. Distillate rate and reflux rate are given 86.8. Distillate rate, reflux rate 1792 kilomoles per hour. Then entry PD1R, PB1R 13 and 55. Exit of D. Okay, here we need to give inputs. So exit stream D is at stage 1 and it's in liquid phase. So here from here you can assume that as exit distillate is exiting as liquid phase, our reboiler is our condenser is total condenser. Okay, it is not mentioned in question, but it is self-explanatory from here. Then exit of S stream is 28 stage. 28 stage. This stream, this S stream is exiting from 28 stage, and its molar flow rate is given to us as 337.8. So here we need to add 337.8. Similarly for PB2R and PD2R also these values are given. So we need to add these three values here. Okay. Then same pressure is given as 110 kilopascal. Ideally here I assume that it should be 120, not 110. Sorry, there is one catch here. PD2 stream is at this stream, this PB2 stream. It is given to us as 177 kilopascal. So I assume that there is some pressure mismatch here. So it should not be here 110, or either this gas should not be 177. Any of the two is not correct. Okay. Then, okay. So our all input are done. So we just need to simulate it. So when we simulate it, obviously our results won't be correct, right? Because our initial gas is not correct. Do you agree? You are not getting anything, or थोड़ा थोड़ा समझ में आ रहा or you're not getting
Sir,
it at all?
sir,
This is very
मैं
complex.
समझ
I
गया.
agree. I agree. This is very complex, but I just that's why I'm just showing it to you. I'm not telling any one of you to solve it. So this is PD2 that our initial gas and PD2 that we are getting. Okay. So we can see that let's just go for mass flow rates. So this is our initial gas, the one that is open right now. So it is 26294.6. It will be same because that is what no. This is the here only you can see that these values are different. 2690.1. Oh, this should be same, but this is not we are getting. Just give me a minute. Let me check here. Did we add it 290 point? It is 290.1 kilomole per hour. And here also it is 290.1 kilomole per hour, but we are not getting exact values. Here, yeah, mole flow rate is correct, 290.1. Okay. If we go for mass, 2424.7 benzene, our initial gas, and it is 2786. So there is difference of all these values. Okay, you can see that there is a difference. There is a difference that what we are getting, and there is a difference between what we are getting and what we assume. Okay, so this was the first part of problem, just to initially guess something and simulate it. For the second part of problem, what do we need to do? We need to perform some iterations. Like what we will do now, we will give this input, whatever output that we are getting from here, we will give it here as input. So we'll just simply copy this thing. So what we will do, I will just show it to you. I will not PD2. So what we will do, this is the results that we are not PD2R, right? Yeah, this PD2R. So what we will do, we will take all the values from here. 108.252. So we will add. Now our temperature is 108.252. Pressure is 1.1 bar. And any of these value, mole flow or mole fraction, whatever you want to take, you need to add it here. And then you need to rerun again. So you will again see that it's not completely matching. There are some mismatches. So you need to repeat this process till the point you are getting both the streams as exact values. Okay, let's not worry about solving it, but did you understand the approach?
Yes, sir.
It is
So it is
very
a bit
different.
complicated, but it is like if you have good knowledge, then you can solve.
Yeah, and you need a good amount of time to solve it. At least it took for me to solve more than 1.5 hours. If you want to try, you are welcome to try. But this is what the reality is. That's what I am trying to show you.
So,
This is what the reality is. Okay. Okay. So I don't have anything else to discuss for now. So if you want to ask some questions or if you are having any doubts, we can discuss something. If you have something to discuss, something to share, we can do that, or we can check this last year's assignment if you want to. I have not checked it, but I don't know if it will be useful for you or not. Okay, guys, tell me what should we do?
so we can solve this assignment
Okay.
question.
Okay, so I will do one thing. I have not solved it, so these questions are I'm also reading for the first time. So let's see. I will keep diagram here and problem statement below. So it is something S3 stream is going to some block heater and it is coming out as S2 stream. We are giving some utility, some price is given. Okay. And some outlet temperatures are given for B3 heater. Okay, there are some inputs are given. Some input and outputs are given. So the problem is figure 1 is relevant portion of flow sheet of a Aspen plus simulation. Figure 2 is the data input palette of utility which upon simulation run yields the result as indicated in figure 3 and 4. Few results have been deleted in figure 4. Next 5 questions are based on that. Okay. The temperature of stream S2 is, what is the temperature of S2 stream? This is the S2 stream
43
and
degrees Celsius.
43.9 degrees Celsius. Okay, we are giving outlet temperature. So it is 43.9 degrees
49.
Celsius. Correct. Similarly, pressure is asked. So it is 1 atmospheric pressure, right? Just check the unit. Yeah, it is 1 atmospheric. The duty result at A in figure 4 is 5 kilowatt. Very easy questions are. Usage. The usage result at B in figure 4 is, what is B in figure 4? Okay, usage. What is usage? How can you get usage? Okay, what is that stream? Let's check. Kg per hour. I guess you just need to convert it.
I think that heat duty we
K
have to divide by 50.
Sorry,
I think we need to divide that
that is
50 into
kilowatt. Yes, kilowatt is kilojoule per second. No, it is
yeah. So we
kg.
have to divide it
Yes.
by the utility heat value, that is 15 megajoule per kg, something like that was given in the utility.
Yeah, it is 50 megajoule per kg. So we need to 50 megajoule per kg. Yes, it is 5 kilowatt. So 5 kilowatt divided by 50 megajoule per kg, and you need to adjust unit for this term. What is the what is for, sorry, what was the unit? Kg per hour. Did you get it? This one is kilowatt. So that is kilojoule per second. And this one is megajoule per kg. So this is basically 50 into 10 raised to 3 kilojoule per kg. And this is 5 kilojoule per second. So 5 kilojoule per second divided by 50 into 10 raised to 3 kilojoule per kg. So it will be kg per second, and you need to convert it into kg per second to kg per hour. Okay? Yes or no? Yes or no? Or should I show you?
Could you show it once?
Okay, I will just
Sir,
show you.
I did 5 divided by 50 into 10 raised to 3 and then multiplied by 3600 and I got the correct answer.
Yeah, you are correct then.
Okay.
Okay. The cost result at C in figure 4 is cost. So what is cost given to us first?
Sir, 0.6.
$0.6 per kg. Okay. So I guess we just need to multiply this value. This is in, I'm sorry, just give me a minute. This is kg per hour. And we have dollar per kg. Yeah, you just need to multiply this answer with 0.6.
Yes, sir.
Can you do it? What is the answer you are getting?
Sir, 0.2160.
Yeah, it is correct, right? Okay. Are you getting it now?
Yes, sir.
Okay, so this is some distillation column. Yes. Stream is passed through the heater, and then distillation column, you are getting one top stream and one bottom stream. Okay, here also something is given. Let's go to the problem statement first. The duty result at A in figure 6 is duty. Okay, duty of red frac. Where can you see from here? You can see duty from here. So that is
minus 69.
69. So answer is no, it's not 69. Yeah, you need to add this. Sorry, heat duty at A. At A is reboiler. Okay, so reboiler duty is not 69. This is condenser. Reboiler duty is 88.82, right? So your answer should be 88.82. Okay, correct. Correct. Then this usage is asked. What will be the usage? What is the unit? Sorry, I just want to see kg per hour. So how can you
The
calculate
kilowatt,
this?
from kilowatt to sir, we need to convert.
But we don't have any other inputs. Uh, Kilojoule per second. Okay, here you need to know molecular weight actually. From there only you can tell. This is a bit incomplete. Okay, you understand. You need to know kilowatt is
Sir, I
kilojoule per
think
second. Yes.
sir here hot utility only again that same value may be required. 50 megajoule per kg.
No, answer is question is different, right? Wait.
I
Okay,
think
yeah, figure 2
utility
is
will
the
be same
data.
for both, right?
Okay. Figure 2 is the data input palette of utility. Okay, so from there only. Okay. So it was 50 megajoule per something. So similar calculation, right? 50 megajoule per kg or yeah, 50 megajoule per kg. And this one is 88 kilojoule per second. So you just need to convert it, right? And cost also similarly, you just need to multiply with zero point 0.6. So I guess zero point 0.6 was the value. $0.6 per kg. Yeah. You just need to multiply whatever answer you get here. You need to multiply it with zero point 0.6.
Yes, sir. 6.339 is the answer.
And then multiply it with zero point 0.6. So you will get cost. So is it 3.8 to
Yes, sir.
3.9?
Yes, sir. 3.837. Yes.
Okay, so these are very easy questions. You don't need to even study anything to solve it.
Yes, sir.
Okay, so this is all from my side. So I don't know if we are meeting again or not. But at this time I'm going to have a revision session. So can you guys tell me what should we discuss in revision session? Or what kind of revision you want? I can prepare some
Actually,
MCQ questions if it's fine. Yeah, please say Asutosh.
yeah, that is fine. I just wanted to ask about that problem of I think 3 4 weeks ago we all had some issues in that
Which
problem
problem?
where reactions
It was not
I can't
converging,
recollect,
right?
but
Some convergence issue.
yeah, yes,
I guess I was also getting the same thing, and the other TA who is teaching on Sunday, he's also getting the same issue. So maybe you can, I don't know what else we can do, but it is some directly issue only. If you wish, you can play with some convergence criteria, like we did it for today. We change it from something to Newton's method. You can try something like that. Anything other than that won't be useful. Everything is correct. You just need to play with some convergence criteria only. You can do that. If you remember in today's lecture for ammonia problem, we we changed that from some standard default to Newton. So you can try it with that. If it works, it works. Okay. 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 I'm not getting any response. Uh, Okay, so can you tell me what do you want for revision session? I can prepare accordingly.
MCQs only, sir, that are there in the assignments, because I guess the exam will be in similar pattern.
Yes, yes. So I'm also thinking of that part. So let's see what I can do. My this session is on 18th. I'm going to have it on 18th because I'm traveling from Friday to Wednesday. I will be back on 18th. So I will be back on 17th. So we can meet on 18th from 6 to 7. I'll prepare some
Sir, we
questions.
can. Okay, sir.
Yes.
Yes, sir.
Yeah, please say.
Sir,
You were
it
saying
works.
something.
It works. It works.
Okay. Okay. So that's all from my side. Thank you so much, everyone, for joining. And thank you so much for keeping it interactive and solving problems with yours with your screen, sharing your screen. It was useful for me too, and it was obviously useful for all of you. Okay.
Thank
Thank
you
you
so
so
much, sir.
much, and please write me back for anything, any queries regarding not just for Aspen, but anything other than Aspen also. I will try to help you out. Okay. Thank you so much, everyone.
Thank you so much.
Okay.
Thank you.
Goodbye and take
Questions
care.
are really helpful.
Thank you, sir.
Thank you. Goodbye, everyone, and take care. Bye bye.
Goodbye, sir. Agashi, Manish. Agashi. Manis.